This is our last lesson in transforming exponential functions. Okay, so far what we've done, we've spent an awful lot of time on exponent rules and on rational exponents. And now what we're going to do is we're going to actually look at graphs of exponential functions. Okay, so this is 3.5. The first thing that we're going to look at is the general equation of an exponential function. And the general equation is y equals b to the power of x, where b has to be greater than 0. So in other words, we're not looking at negative bases here. That doesn't mean to say that we can't have something flipped over, but we'll talk about that in a moment. Okay, so this is the general formula for an exponential function. So the difference being, compared to other functions, we've never had before the one variable as an exponent. So that's why it's called an exponential function. So the first of all, we're going to look at two different kinds. The first kind, we're going to look at a function that's increasing. So you can see the graph here that it's y equals 2 to the power of x. And it's an increasing graph, which means if I read from left to right, it is increasing. It's going up. Okay, so that's what they mean by an increasing function. So the first of all, in order for it to be increasing, our b value in our general formula has to be greater than 1. Okay? The next thing that we notice is we call this often exponential growth. Okay, and there's lots of practical applications for exponential growth in our world, so that's one reason why we study it. We also have a horizontal asymptote at y equals 0. So in other words, it doesn't touch this x-axis. Okay, it creeps along it, and if you actually take the graphing calculator, which some of you did when you did the graphing calculator activity, if you did the trace and you kept tracing back and back and back, the y value gets close to 0, but it flips into scientific notation, and it, in all intents and purposes, it does not ever touch the x-axis. The other thing that we know is that it has a y-intercept at 1. Okay, so right at 1 we have the y-intercept. The other thing that we should know, and I think there's another one, and it doesn't want to show us, and that is its domain and range. So the domain, x can be anything, so any real number. The range, however, y can be anything. However, y has to be greater than 0. You can see that we're never going to get to the negative values of y. Okay, the other kind is what we call when a function is decreasing. And this is what it looks like. Okay, so again, if I read from left to right, the same way as the book, you can see that it is going down, it's decreasing. And the way we get that is the b value in the equation has to be between 0 and 1. Now, in your graphing calculator activity, when b equaled 1, what you ended up with a horizontal line through the y-axis at 1. We call this type a decreasing exponential decay. And there's financial aspects to that as well as real world. In the natural world, we again have a horizontal asymptote at y equals 0, in other words, the x-axis. The y-intercept also is at 1, so that is something that they have in common. And if we look at its domain and range, the domain again can be any real number. However, the range also needs to be greater than 0. Okay, so that is just a general recap of exponential growth, exponential decay. So let's actually look at some kinds of examples when we're transforming them. So like other functions we've studied, exponential functions can be transformed in the same way. So if I look at this one, first of all, remember we talked about parent functions? Okay, so in this case, my parent function would be what my base is. So my parent function here would be y equals 3 to the x. Okay, so 3 to the x. So again, I know that I go through 1, and I'm just going to zoom this so we can have a better look at what's going on actually on the grid. Okay, so what I've done is I've just made the diagram just a little bit larger for us. And let's actually go now and actually do some of this graphing. So as I said, it has a spot at 1. And when x is 1, we have 3 to the power of 1, which is 3. So 1, 2, 3. And then when x is 2, we have 3 squared, which would be 9. So what's different about these types of graphs is the sense that what's going on with them is, what's going on with them is each parent function is different depending on what the base is, the b. So the b here is 3. So now if I go 3 cubed is 27. Notice how quickly that has climbed now, and that's one nice thing about exponential. 8, 7, so it should be right there. And if we do 4, 3 to the 4th, which would be 81, which is off my graph. If I go and look at -1, so 3 to the -1, remember negative exponent, I would flip the base so it's 1/3, and you notice I'm going to have a really hard time graphing it. It's just before the x-axis. So here is my parent function for this graph they're expecting me to graph, and for some reason you'll have to excuse my pen doesn't want to go where I want it to go, so I'm going to switch to going to switch now to my mouse just so we can see what's going on here. So if I draw a smooth curve, and then it's going to creep as close as I can to the x-axis, which is kind of difficult using the mouse. So that's the parent function. Now what they're asking me to do, remember, if I change the x, it moves it left or right, and it always moves it in the opposite direction. So here it has x minus 4, so it means I'm going to move all my points 4 units to the right. Okay, so 4 units to the right, and we'll just type that in, and we'll use it in blue. 4 units to the right. And also our +2 means that the whole graph is moves up 2 units. And I'll just move that over so you can see that. So usually the easiest thing to do is to translate these points following this pattern. So what we're going to do is I'm going to take a blue one this time. And normally this points at 1, so I'm going to move it over 4 units and up 2. Okay, so what I've done is I have, and I'll bring up the magic pen, is I've taken this point and I've transformed it to there. Okay, the next point I'm going to transform, obviously, is the next one, which was 1, 3. So now it's going to be over 4 units. Notice what happens. I don't have 4 units, and then up. So let's go back the other way now. Remember, this was at -1, so 1, 2, 3, 4, and then up 2, so 1, 2, and so it was 1/3. So what's happening is I'm going to now be creeping along this line here, and then I'm going to be going up. So what's happened is there was an asymptote line originally at, oops, sorry, I didn't want that one, at the x-axis. Now what's happened is I'm having one that is going to be located along here, which has the coordinate y equals 2. So it's changed my asymptote line. Okay, so if I look at my domain and range, which this question didn't ask for, but let's add it anyways, And I will do it in black, and we don't need it quite that large for you to see it. So for our new one, what's happening for our domain and range is our domain is going to be obviously the set of real numbers, and that doesn't change. I'll just try to get, where are you? And our range also is going to be the set of real numbers. However, what it has, remember, it has an asymptote line, which means we have to make sure that we put the right sign down. And you have to excuse me, it just takes a little bit to get this done. So real numbers, and we have such that y in this case has to be greater than 2. Okay, not equal to 2, because remember that's an asymptote line. So it needs to be greater than 2. Okay, so it's actually, since we've done an awful lot of work with functions and transforming them, actually this is fairly easy now, or it should be. Okay, now let's look at another one. This time we have a decreasing graph because we can see the parent function has changed, so that typical equation that we had before, the general equation where it was y equals b to the x. This time we can see that our b is less than 1, but it's also greater than 0. So again, we know it's going to go through the y-intercept of, and I better put y, and this is x, the y-intercept at 1. And this time, if I'm going to go backwards, so when 1/2 to the power of -1 would be 2, 1/2 to the power of -2 would be 2 to the power of 2, which would be 4. Okay, and if you notice, it's easier to do actually backwards. Okay, so I have the left side of my graph. Now the right side, when I have x is 1, 1/2 to 1 is 1/2, and then it's going to go to 1/4, and then it's going to go to 1/8, and it's going to just creep along there. So this is going to be our parent function of y equals 1/2 to the x. And also I need to draw my asymptote line, and it is along the x-axis. So now what they've done with this, they have put a -3 in front of here. So what that means is every single one of these points is transformed by -3. So instead of being at 1, it's going to be at -3. If there was just a negative here, it would be negative in front of all these points, and all these points would then move down. And you could actually graph in more than one thing. So if I did, in this case, now I'm going to do y equals -1/2 x, and then we'll do the last part so you can see what I'm talking about here. So what I'm going to do is I'm going to stop before I start transforming these, because I am going to run out of time. It won't take us very long to finish this question up.